Thank you very much for the introduction, and thanks everyone for coming to this talk. The title is a little bit different than what's on the FPSAC website, 'cause the name of this talk has changed a little bit since I originally came up with it. But thanks to Art Duval for coming up with the name Multi-Ejections when I posted on Facebook, trying to figure out a good name for this thing. So I'm going to be focusing mainly on a geometric construction that is necessary for the results that I prove in this paper, more so than really saying exactly how this construction is used, because the construction's pretty and it's uses a lot of linear algebra. There's not too much deep mathematics involved. And I think that there's more it can say. So I'm really interested to hear if anyone has ideas of where to go next on this project. So I like examples. So I'm going to start immediately with an example where M is going to be a 2x2 matrix. It's going to be this 2x2 matrix. And if we think of it as a map from Z2 to Z2, then the co-kernel of M is going to be this group Z2 divided by the image of M. And the way I like to think of that is that you take all the points in Z2, and then if you can get from one point to another by adding integer linear combinations of the columns of M, then the 2 points are equivalent. So like all these points you can get to by adding integer linear combinations of the first column, and then you can get to these points by taking the second one, and we get this whole lattice of points that are all in the same equivalence class of this co-kernel of M. And if we did this a bit longer, then we get something that looks like this, where you have 6 different colors, one for each equivalence class, which is telling us that the size of that co-kernel is 6. And they form this structure, and I drew for one of the colors, I have these parallelograms that you get the same pattern for all the different colors, but this is just showing you how all of the elements of the same equivalence class are related to each other. And a question we might ask is, okay, so we have these 6 equivalence classes. Can we actually get a set of 6 elements where there's one for each equivalence class in some natural way? And this will help us in the future also. So a way that we can do this is we take one copy of a parallelogram and we're going to choose some generic direction to nudge all the points. So we could say, shift them in this direction. And then we just check which points are going to get shifted into your parallelogram. So in this case on the left, we have these 6 points, and we'll notice that there's exactly one of each of the 6 colors. So this gives you a way to get a set of representatives for this co-kernel. And if we chose a different direction, we would also get 6. We would also get one of each color, but potentially the stuff on the boundary could switch. And we just have to make sure that whatever direction we choose isn't parallel to the sides of the parallelogram, and this will always work. So this is how the co-kernel works and how we can find representatives for that. So next I want to introduce a notation. I'm going to use pi dot for the parallelepiped formed by the columns of M. So this is just, you take the columns of M, you do 0 to 1 multiplied by each one, and you get this higher dimensional analog of a parallelogram. And it's well known in linear algebra that the volume of this parallelepiped is going to be the determinant of your matrix. And if we want to compute this determinant, we're going to get that it's the sum 2 plus 4, which is equal to 6. And in fact, this 6 was what we had before. There were 6 colors. 6 is the size of the co-kernel of M. And this is always going to be true, that the determinant of M is going to be the size of the co-kernel when M is a square integer matrix like this. And something that we're going to think about that probably seems a little unmotivated here, but in the context I was doing it made a lot of sense, is so we have this 2 and this 4. Is there a way that we can take these 6 equivalence classes and associate 2 of them with this first summand and 4 of them with the second summand? So keep that question in mind. And now I'm going to do a construction. So we take our first matrix M, and I put a little dotted blue line in the middle of it here, and everything below the blue line, I'm going to turn negative. And then what I'm going to do is I'm going to take one element from the top part and then the other column element from the bottom part and turn everything else to 0. And you can do this in two different ways. We get these two different pieces, and I'm going to take their fundamental parallelepiped, in this case parallelogram, in this case I guess rectangle and square, and I'm going to call this the tile associated with M and write T of M. So for this particular example, let me just draw this one out. So let's say that this point is the origin. Then our first parallelepiped, we're going to go 1, 0, and 0, -2. So we get this rectangle. And then for the second one, let's just use a different color. We're going 0, 2, and 2, 0. So we get these two pieces. They are only going to overlap on their boundary. And together, this is going to be the tile. So the tile in general is going to be a non-convex polytope that is the union of parallelepipeds. And so the cool thing about this tile is it is going to periodically tile the plane. But not only that, the lattice that you had translated by to get this tiling is precisely the lattice given by M. So you can see these parallelograms are the exact same parallelograms from before. So we're shifting the shape by the same amount that we shifted that original parallelogram, and we get this tiling. And you can see on the bottom here, it's pretty immediate to see, oh yeah, these are the same volume, but it's even a little bit cooler than that because this purple part at the top is going to shift by 1, -2, which is the first column of M to get here. Whereas the blue part is going to shift by 2, 2 to get over here, and the other stuff isn't shifting at all. So really these two shapes, if you sort of mod them out by the lattice given by M, they're going to be exactly the same. And this is the important property that's going to give us our multi-ejection when I explain what that is. So what do we do now? So what we can do is exactly what we did before, where we take one copy of the tile, we choose a sufficiently generic direction vector, and we shift all the points in that direction. And this is always going to give us 4 points associated with the square. You can see these 4 points, and 2 points associated with a rectangle. And furthermore, these 6 points are all going to be distinct as elements of this co-kernel of M. So this is a way of getting a set of representatives where we have 2 associated with the smaller piece and 4 associated with the larger one. And it might change based on our direction vector, but we're always going to get 2 for one and 4 for the other, exactly matching this 2 and 4 from down here. And in general, this is what I'm going to call a multi-ejection. So it's like a bijection to a multi-set, where we're mapping from the co-kernel to the summands, where it's not that we want like a 1-to-1 correspondence, we want the pre-image of each summand to be of a very specific size. And this multi-ejection construction is going to work for more complicated matrices. So I'm going to give you a couple examples of some larger matrices we can work with, and then I'm going to talk more about the motivation for this. So this is the #1 example I worked with most when I was playing with this theory and trying to come up with these ideas. This matrix right here, and I'm going to draw this dotted blue line here. I guess when I say here, I should actually mark it, but you can see the dotted blue line. And in this case, the co-kernel is going to be Z3 divided by the image of M. And if we do a Laplace expansion for the determinant on this bottom row, we're going to get this sum 1 + 4 + 9, which is giving us 14. And the important property that's going to make the construction possible is that all of these terms have the same sign. So we're really adding these 3 things together, and that is going to mean that we can make a tile. So how do we do this? It's the exact same construction, essentially. So everything below this dotted line, we're going to make negative. That's the first step. And then the second step is that we're going to take, and this time we're going to take a 2x2 matrix of the top part and then the remaining part on the bottom. So we have this 2x2 and then this 2x2 and this 2x2 and this. And everything else becomes 0. We take these 3 pieces and take their union of the fundamental parallelepipeds, and we get something that looks like this. So thanks to Marielle Sapina and her brother for 3D printing this for me. But this is the tile that we get for this particular matrix. And as you might guess, this is going to periodically tile space. And the translation lattice that we're going to do exactly comes from the columns of M. And we can see that from this video I made here. This I made using the Blender software, which I recommend to anyone looking to make like computer animation stuff. This is a very powerful free software. And if you watch enough YouTube tutorial videos, then you can make something like this. So you can see that this is in fact going to tile all of space in a periodic way. And we can also create these multi-ejections in the same way where we choose a generic direction. 1 point is going to be mapped to the square, 4 will be mapped to the red region, and 9 mapped to the blue region, and they're all going to be distinct representatives of this co-kernel. And we can do this in even more generality if instead of just having one row that we do the Laplace expansion for, we can do multiple rows at once. So there's this formula for multiple row Laplace expansion. You just have to be careful with the signs. And for this particular example, we get the sum of terms that are all non-negative when we're calculating the determinant. And that means that we're going to be able to do this construction. So I'm going a little fast here because it's just more of the same, but everything below the line becomes negative. And then we're choosing a 2x2 from the top and the sort of complementary 2x2 on the bottom. Technically, we could ignore this one because it has determinant 0, but this will give us our tile. And then we can, we'll periodically tile for space using this matrix as our translation. So what is the motivation for this? So I want to start, so there's this result by Marino back in '99 that the size of the sand pile group of a regular matroid is equal to the number of bases. This is a generalization of a similar result on graphs and spanning trees, but you prove it using a generalization of the matrix tree theorem. And in 2017, Bachman, Baker, and Yuen defined natural bijections or even free transitive actions of the sand pile group on these bases. And this was presented at the first FPSAC I was at back in 2018 in Dartmouth. So this is a lot of these words, I'm not going to explain what they are. If you're not familiar with them, it's okay. But the idea is we had this relationship between the sand pile group and the bases, and it took a little, and the proof gives a numerical result, but then it can be extended to get a bijective result. And so you can extend this instead of working with regular matrices. Another way to extend it is to work with cell complexes. So in '83, Kalai explored spanning trees of simplices, found that there's this weighted count for the number of spanning trees of a simplex. This is something that Vic Reiner actually talked about in the reflections workshop for anyone who was there last week. But this was extended by Duval, Clivens, and Martin, who showed that the sand pile group of a class of cell complexes is the weighted sum of cellular spanning forests. The proof was using the matrix tree theorem generalization. And I'm not going to say what all these things are, but the sand pile group is always a co-kernel, and the cellular spanning forests relate to these summands in a natural way. So the question of Clivens was, can we elevate this numerical relationship to a multi-ejection? And the answer is yes, precisely using this geometric construction I've given. So what is the theorem? So if we start with a n by n square matrix, where these two submatrices have complementary orientation, which I'll talk more about, but for now, it means they have the summands have the same sign. Then this tile is going to periodically tile Rn with respect to our lattice. And if we choose a sufficiently generic direction, we're going to get a multi-ejection between the co-kernel and the summands of this Laplace expansion, which summands of Laplace expansion are related to generalized spanning trees, or related to bases of matroids. It all kind of connects together when you look at it in the right way. So there's a theorem by Chaikin from '96 that actually gives some equivalent conditions for when two things have complementary orientation. So the second one is about oriented matroids and duals. If you're familiar with matroids, that might look very friendly. If you're not, then that's okay, don't worry about it. But the other condition that was really helpful when I was trying to prove this stuff is that this is equivalent to K1 and K2 having no common non-zero covector. So if you take any linear combination of the rows of K1 and the rows of K2, they can't have the same sign pattern, no matter what. And this is equivalent to having complementary orientation. So it's not just some weird thing where you need to write out the full Laplace expansion and see if all the terms are additive. There actually is a natural way of looking at this. And there's also specific matrices that we can work with where this is always going to be true. So that when I was originally proving this and working in the cell complex and Sampao group case, I was mostly working with these matrices. So K1 is going to start with the identity, and then it's just going to have some matrix of integers on the right. And then K2, we're going to start with the transpose and then have negative identities. You can see K1 and K2 here. I actually used negative K2 for most, I think in my paper, I use negative K2, and a lot of times that's more common to see in the literature too. In Oxley's matroid book, he talks about how this represents the dual matroid. But the advantage of using K2 as defined here is that M becomes symmetric. And I'll talk a little bit about that. But the important thing is that K1 and K2 are always have complementary orientation. So we can always construct a tile, and we always get one of these multi-ejections. And in more generality, if we start with two matrices whose corresponding minors match in sign, so for example, we could have K and K hat be the same matrix. That's a lot of what happened in the Sampao group case. Or we could have both of them be positroids of the same rank, for example, or represent positroids of the same rank, people interested in that. Really anything where their minors match in sign, where zeros are okay. And then we're going to find a new matrix that represents the oriented arithmetic matroid dual to K hat. And I'm not going to tell you exactly what that means or how to do that, but I will say it's always possible. It's not always unique, but it is always possible. And I talk about that in my thesis. And then now K hat prime and K have complementary orientation, so we can find our multi-ejection. So this is a general method that we can use to get two matrices of complementary orientation. And I also want to talk about a lower dimensional tiling result. So this is the matrix from before that we couldn't actually draw the tile for because it was in 4-dimensional space. But you can actually take the number of rows in K1 or the number of rows in K2 and project down to that size. And what happens is the top part of your matrix is going to give you sort of the vectors that make up your parallelograms. And then the bottom part is the determinant is going to tell you how many there are. And there's some more complicated stuff involved in exactly how the construction works. But the nice thing is we still get this tiling in exactly the same way. So we can like do this and this and this, and we get this tiling of the plane, and we could just work in this lower dimensional case instead of going to higher dimensions too. There's like one condition we need, that the GCD of these, the lower minors of the matrix have to be 1, but as long as that's satisfied, we can go to this lower dimensional case. And something I'm curious to explore more is, I conjecture that every tiling of space in this way using parallelepipeds can be corresponds to some higher dimensional tiling. And I think that I can use that to classify the tilings of lower dimensional space, but I haven't been able to prove it yet. So it's a conjecture in my thesis. And I also want to talk briefly about rows and columns. So one of the biggest challenges for generalizing my initial version of this result is I was working with a co-kernel of M transpose instead of the co-kernel of M, because it made more sense to look at the lattice of rows than the lattice of columns. That had more of a connection to this sand pile group I was considering. But I realized that when I wanted to generalize, I should actually work with a co-kernel of M. And the reason why I was able to get results in my specific case for M transpose is because I was working with a matrix that was essentially symmetric. And I want to, and so these two groups are going to be isomorphic, but they're non-canonically isomorphic. They're actually Pontryagin dual to each other, thanks to Vic Reiner for telling me what that meant. And there's some interesting things that can happen where, for example, I have these two matrices here that have the same co-kernel. These two groups are exactly equivalent. You can see that because the lattice given by the columns is equivalent. But if we take the transpose of the first matrix, then we're going to get a new matrix where the co-kernel is no longer equal. They're isomorphic, but they're not equal to each other. Whereas if you take the transpose of this other matrix, it's just symmetric, so it stays the same. So there's the stuff that you think might work that doesn't work when you're dealing with these transposes. So it's just something to work with more, and it seems like this duality is really important. So now I just have some further directions that I have a couple minutes, so I'll just briefly talk about these. So I mentioned positroids as a way that any two positroids, the positroid and the dual of a positroid are going to always have complementary orientation. So there's something there. Toric varieties, I see them show up all the time. I don't know too much about them, but I know that they use integer lattices a lot, and I'm wondering if there's some connection. I'm also curious about generalizing these ideas to the case where we don't have complementary orientation. I was looking at some cases where it seemed like you might get like a tiling that has overlaps, but then the overlaps are precisely the stuff that's negative. And I was looking into that, but I haven't gotten too far. And then getting back to this Pontryagin dual. So I mentioned how the sand pile groups were normally working with the co-kernel of a transpose of a matrix, but we could work with the co-kernel of, or we could work with a Pontryagin dual of that, and what do we end up getting? That's an interesting question to ask. Another question you can ask about the Earhart theory results about the tile. It's a little bit weird because the tile is generally non-convex, and typically when you're doing Earhart theory, you're working with convex things. So a couple of the approaches I was looking at got weird for that reason, but you could definitely try to look for some more stuff. And then more of what I was saying about classifying periodic tilings using rational parallelepipeds. I think there might be a way to use this result to classify those. So thank you very much for listening.
Thank you. That was very nice. Lots of cool pictures. I enjoyed it very much. Questions? So Joseph has a question in the chat.
All right, let me see. Tiles be further subdivided. That's a good question. I haven't thought about that yet. So I think that your guess would be as good as mine, but there definitely could be something there to further decompose them. Thanks.
Other questions? Maybe someone typing. Or just it's getting late in the day. All right. Well, let's thank the speaker again for this beautiful talk. We have a couple of minutes before, so the next talk will be at 5 past. So we have time for a quick break, or of course you can use the time to ask more questions in the chat. See you in 5 minutes. And thank you again, Alex.